B6. B6 now, you're given a reaction, right? So it's 2 moles of phosphorus react with 3 moles of, oh man, I did a terrible job. I didn't do those superscripts. I feel really bad now. 3 moles of chlorine gas to form 2 moles of phosphorus trichloride gas in that case, right? And so that reaction, as it's written, releases negative 574 kilojoules. Based off of that, right, we're going to answer a few different questions. Question 1, how many moles of phosphorus are needed to produce 488 kilojoules of energy? So the thing here to think about, right, is that as the reaction is currently written, right, for every 2 moles of phosphorus that are used, you're releasing 574 kilojoules. And so if we wanted to standardize that down to what the energy should be per mole of phosphorus, right, all we have to do is just simply divide it by 2 in that case, right? So if we take the delta H of this reaction right here, that'll just simply become negative 574 kilojoules, right? That's going to be divided by 2 moles of phosphorus. And so what we get there is 574 divided by 2 is 287, negative 287 kilojoules per mole of phosphorus, right? So we have that right there, right? So we know now how many moles of phosphorus we need in that regard. So now the question becomes, how many moles of phosphorus do we actually need then to do 488 kilojoules? And so to do that, right, all we have to do is to figure that out, right, is going to be the delta H is going to be equal to the number of moles times the delta H of the reaction where it's standardized to those number of moles. We're trying to figure out what N is, so all we have to do is just rearrange this. We get delta H over delta H reaction. And so what we're trying to figure out is, to get negative 488 kilojoules, right? Divide that by negative 287 kilojoules per mole of phosphorus. And so what we get then is 488 divided by 287 gives us 1.70 moles of phosphorus, right? So that's how many moles of phosphorus we need in that case. Let me just double check that. That's what I got on the key. Yep, 1.70 moles of phosphorus, right? So that's all you have to do for that one right there. Is you just simply you're standardizing that reaction to the number of moles in that case. We're going to do the same thing for part B, right? So now it asks how much heat is released when 122 grams of phosphorus trichloride are produced. And so in this case right here, right, the first thing we want to do is we want to standardize that reaction to 1 mole of PCl3. And so now, right, so the delta H of the reaction in this case is going to be equal to negative 574 kilojoules divided by 2 moles of PCl3, right? So we have 2 moles of PCl3 that are being formed for each, for that reaction right there. So what we get, same thing as we did for the previous one, right? So that should be negative 287 kilojoules per mole of PCl3. Right, so that's now standardized. And so now the question is, right, like how much heat is released, right? And so Q is going to be equal to delta H in this case, right? So Q is going to be equal to the number of moles times the delta H of this reaction, right? That's standardized to the PCl3. So we know how many, the next step we have to do now, right? We're not given how many moles it is, right? We're only given what the mass is, 122 grams. And so the next step that we want to do is we want to figure out what the molecular weight is of PCl3. So the molecular weight is, and I'm going to cheat right now. I'm going to look it up because I don't remember what phosphorus and chlorine the molecular weights are. PCl3, it's 137.33 grams per mole. So Google is very, very helpful with a lot of those things. 137.33 grams per mole, right? That's the molecular weight. And so then now the number of moles in this case is going to be equal to 122 grams divided by 137.33 grams per mole, right? Grams cancel, moles goes up. So what we get is 122 divided by 137.33 comes out to being 0.888 moles. So we know now how many moles of PCl3 we have. We can throw that into this equation, right? So we have 0.888 moles of PCl3. Multiply that now by the delta H of the reaction that we had standardized earlier, right? So that's negative 287 kilojoules per mole of PCl3. So we get all of that. So now Q is going to be equal to 0.888 times negative 287, right? Comes out to 254.8, right? Which is 255, right? Is negative 255 kilojoules, right? And so that's 255 kilojoules that are released in that case, right? So if it's a negative, right, your system's going to be losing that energy in that case, right? So that's getting released to the environment. So that's how you do part B. Part C, how many grams of Cl2 gas are needed to produce 27 kilojoules? Again, very similar setup, very similar approach to what we did for A and B. So the first thing we want to do is we want to standardize now that reaction to the number of moles of Cl2. And so now, right, the delta H of this reaction, I'm just going to block all that off. Delta H of the reaction is going to be equal to negative 574 kilojoules, right? That's going to get divided by now, right? That's being produced for 3 moles of Cl2. So divided by 3 moles of Cl2. And so what we get then is that in the per mole basis of Cl2, we have negative 574 divided by 3 comes out to negative 191.3 kilojoules per mole of Cl2 in that case. Right. And so we have that standardized now. Now the next step is to do the same thing that we did with A, because now we want to figure out how many moles of Cl2 we need. Right. And so now we know that we want to have the delta H in this case, right, is going to be equal to the number of moles times the delta H of the reaction. And so we rearrange this, right? What we get is N is equal to delta H divided by delta H of the reaction. And so that comes out to being 27.0 kilojoules divided by, that should be negative 27, right? Because we're producing it, we're releasing that amount, divided by negative 191.3 kilojoules per mole of Cl2. And so what we get then is, so negative 27 divided by negative 191.3 is 0.141 moles of Cl2, right? That's the number of moles that we need in that case. We're trying to figure out what it is in grams, and so we want to figure out what the molecular weight is. So the molecular weight of chlorine gas is, I think it's like 70, because I think it's 35.45, I think is the molecular weight of a chlorine atom. And so let's see, how close am I? Do I not know how to read anymore? There's too many things. Oh, I should probably just type in chlorine gas. 70.90, yeah. So, yeah, 35.45. I guess I do know it off the top of my head. There's some that were the molecular weights that I've remembered, but then some I don't. Anyways, so we know the molecular weight is 70.90 grams per mole, right? And so now we're just trying to figure out what the mass is, right? And so the mass is going to be equal to the molecular weight times the number of moles. And so that's 70.90 grams per mole times 0.141 moles in that case. And so what we get is 70 0.9 divided by, or not divided, multiplied by 0.141 comes out to being 9.997 grams, which I think is what I have. 10 grams. Yeah, exactly. Same thing. Right. And so that's how you do that, right? So that's the setup. So one important thing always to think about is that sometimes reactions are given as like delta H, where you have like, joules per mole or something like that. You have to figure out what that mole part is like related to in that case, right? Because you can standardize them to different amounts of moles in those scenarios, right? So in this case right here, right, that's all we were doing for all of those different steps. So yeah, so that's everything that people had voted on.